Okay, this is going to be the last presentation about chip removal or machining, and I'm combining several topics that I don't normally combine, but I wanted to get this out in a timely manner. It's mainly going to be about computer controlled stuff, but before you can get to understanding computer controlled equipment, you have to talk about work holding. Now, work holding has two purposes. One is to clamp it, to hold it in place. You don't want it getting away from you. You don't want to crush the part. The most often in a mill, it's the vise, and you can attach dial indicators to measure movement. On a lathe, of course, it's in the chuck. It's going to hold the material. And when you watch the milling show and tell video, you saw that you have the T-slots and the dogs and the bolts, and you can lock stuff down straight to the tabletop. It's with those T-slots and bolts that hold the vise in place. You can also use V-blocks I've mentioned for round tubing, just all examples of clamping it down. The second purpose of work holding is to locate it. And the system inside the work area of a mill, lathe, or any other device is broken up into a Cartesian coordinate system, X, Y, and Z. Good old Rene Descartes, maybe you've heard of him, came up with the system. And you're most familiar plotting algorithms logarithms or plotting curves on simply an X and Y axis. But manufacturing machinists go one step further and add the Z axis, so that any spot within the area that can be cut, can be used, is you can identify it by giving it the X, Y, and Z coordinate. Now you've got to set a 0 for that, so you've got to use an edge finder. You've seen that in the video about milling, and the one on CNC that's going to be posted with this module. So what we've done so far in terms of holding stuff down is we've looked at the 3-jaw chuck, the machine vise on the milling machine, and the manual measuring method using a dial indicator. Every time that little lower arm is moved, the dial at the top moves a little bit coordinate. And that becomes very handy to get to very specific places. Now, for holding the cutting tools, you've had the drill chuck, you have the R8 collet, and the drill chuck could be on a mill, it could be on a lathe, it could be on a drill press, very common tool holding device. Before we go a little bit further, I want to make sure you understand a few terms. A fixture is a device usually customized to hold a workpiece when you're going to make multiple parts. When you see the little CNC video, you'll see that in the vise is a little clamp with 2 pins in it and 2 hold downs, and that is simply to be able to put the pieces in there to make the parts. A jig takes it a step further. It generally has some sort of guide built into it, but you'll often hear jigs and fixtures, and sometimes the terms are interchangeable. Then there's this tombstone. I'll show you a picture of that, but it's a fixture with multiple fixtures or jigs or positions, and you'll see. Need to define home and zeroing. Home is going to be the 0, the position of 0, 0, 0 for the space within whatever the machine area you're going to be dealing with. Now, you might have the machine home, and that's going to be the default. It'll be some sort of sensor usually, or it'll go all the way to one side or the other and define that's where it's going to be. Then you'll have a fixture home, which is often touched off against the part of the fixture, device, or whatever, to say, here now we're going to be working with that. Again, we'll see it when we get into the programming part. And zeroing is the process of finding that edge. Remember that to find a point in space, it can be defined by the intersection of three planes. And that's exactly what's happening here. You're going to have one plane that defines the y-axis, one plane that defines the x-axis, and one plane that defines the z-axis. And where those planes intersect is 0, 0, 0. Here's a tombstone. One on the left is just a blank one. You could bolt down all the different kind of parts to it. You can see on the right how they've done that. And then you put it into the machine and it does what it needs to do. Now, I'm going to mention one thing here from a financial basis about how small machine shops or manufacturing shops make some money, how the business is run. If you look over on the right, you've got, let's say, one face of that tombstone might be leased out to the company that gets those little triangular parts or octagonal parts or whatever. Now the other side would be leased to a company that makes the square parts. And so they don't, it's more to it than simply making a something easier for the machine shop to make the parts easier. If they know that they're going to make a lot of these parts, they will frequently go back to the customer and say, okay, we're going to lease or sell you a part of our tombstone. Nobody else will use that. It'll be only for your purposes, and we will be able to slap your parts in and have a turnaround time to improve our turnaround time. But what you need to do is pay us to make this space available for you in the future. And so by leasing part of the face of the tombstone, they help the customer get parts quickly, and they are able to, with faster turnaround time, they'll reserve it. So a company will have 15 or 20 of these tombstones, and you see the big hook at the top. They're heavy. They got to be moved by a crane. But customer needs some of their parts, they can whip them out right away. And just in case you thought otherwise, those tombstones could be mounted horizontally. And again, the financial advantage is that the tombstone could be owned, partially leased to the customer whose parts the machine shop is making, and they can get some advantages that way. Okay, as I mentioned, to use the tombstones, use any fixture, to use any machine particularly with computer control, you've got to find the zero. Now you can do it by a mechanical edge finder. That's the thing over on the left. That's one kind of we're using. And that little tip on the left is attached to the body with a combination spring and magnetic attachment, and that can slide a little bit either or. You can do it a couple of different ways. You can put it in and have it off center, and as soon as it centers up, because you're touching the bottom part to the metal, of course it's not laying at that angle, it's of course straight up, but it's hard to, it wouldn't fill the page very well here. And as soon as it runs up against the metal on the edge that you're trying to zero, it will line itself up and move smoothly. If you go a little too far, it gets out of whack again. So you can find exactly where declare a particular space to be. This is exactly in line with the spindle in this plane, except that you've got to take into account the diameter of the tip, which in the case of this one is 200 thousandths. And that ends up being you can get them with the bigger ones, but so you move it over, subtract 100 thousandths, and you've got it zeroed. You can also get an electronic edge finder and this is very common on computer controlled equipment, so that the machine can bring its head or bring a table into position, and as soon as it touches something and get electronic beep, it knows that's where it is, and it will sometimes check 2 or 3 different sides, and it will do the mathematics within the machine, but it's doing essentially the same thing. And you can get ones with lasers that will identify the corners. And in fact, one of the faculty members in the Department of Industrial Technology from Fresno State has a little business, and he makes and sells these laser edge finders. Just as we defined a few terms earlier, we had a few more to define. And you'll hear the terms CAD CAM. Well, CAM is all the computer-aided parts of manufacturing. And there's a whole bunch. The machinery, the inventory, all kinds of stuff. CAD has to do with computer-aided design. And you make your part, and you drive and ship your parts. And they're now drawn on a computer. You could have a process that just uses CAD, but not CAM. But you can't have CAM without the CAD. In fact, the way that we're doing it in this class, we're using CAD because those drawings that you see are computer aided in design, but we're not using computer operated machines. We do have one, and you'll see how a part is made for that. Now, how does this all work? Well, your CAD program, you can export the drawing and run it through a separate program, and it will generate the G code. Now, that stands for Go code, and it is simply text, and it's one line at a time. You can think of this as an algorithm of how it's going to make the part. Before we go a little bit further, a few more definitions, and then I'll show you some G code. You see here the term CNC. That stands for Computer Numerical Control. And it's the machine that takes the algorithm that the CAD program put out, the G code, and then actually operates the machine. Now, do not confuse this with the digital readout. We have 2 digital readouts, and when you crank the table, you see the numbers change to locate the various positions on the X and Y axis. It doesn't give us the Z axis, but traditionally that's not quite as critical in a manual operation because you can set that quite easily. And what these CNCs have motors that drive the parts, or the cutting tool, or the table, or whatever it is that they're operating, into the same position that an operator would use by turning cranks and wheels. The big ones use AC servo motors, very high speed, high torque, but harder to coordinate and operate. Sometimes they use stepper motors, a little bit lower cost, typically not as robust, but easier to program. A stepper motor is a motor that is given a number and it says how many turns to make based on dividing the arc of the rotation up into segments. AC servos work once they are programmed. They just give it electricity and it goes. But when they're programmed, they are given a specific place to go and typically told how fast to get there. Now, CNCs are also going to have other sensors. They're going to have sensors that will check to make sure you're not running too far off the table. You can have sensors to locate home positions, maybe to pick up new cutting heads, all kinds of different things. Now these axes, you'll hear 3, 4, 5, 6 axes. What that means is a 2-axis, is, you remember from the lathe, you can go in and out or down the part. You can't, those are the 2 axes that you have. Now the mill, you have 3, and from the operator's position, left and right is the x-axis, up and in and out is the y-axis, and up and down is the z-axis. Okay, 3 axes. How can you have 4? Well, you could rotate the table or the head automatically, of course, but you could do that on the, you could rotate the head on the Bridgeport, and so you can change how it rotates. The 5th axis would be to take that 4th axis. Imagine moving the table and you're rotating it along the y-axis. It just rotates like a big, you can tilt it forward, tilt it backward, tilt it forward, tilt it backward. Well, imagine now if you actually are able to lift one side up or the other side. Actually, it's the other way around. The 4th axis, you lift up one side or lift up the other side. And then the 5th axis would be rotating the table. So you can get all kinds of different adjustments. You'll see some, I tried to pick machines in the videos that had some interest. Okay, let's get into some G-code. G stands for go, and there's a G and then a 1 or a 2, or it could be a bigger number because there's all kinds, and this has grown a lot, and still new features are added. But if you are going to a particular place, you would give it the X, Y, and Z coordinate of where be it the head, be it the table, be it whatever, you're getting the cutting point to that spot. For example, in that first line you see G1, X 1.20, Y minus 0.75, and Z 2.78. That spot, now the minus sign with the y-axis means negative. Go past 0 to the Z to that spot on the y-axis. And remember, 3 planes determine a point, and this is telling you to go to that point. If you had a line and it only had the Y and the Z, it would keep the X the same. So you would be running in a kind of straight line. You got other things. G2 says go clockwise, so you can make an arc. Go 3, go counterclockwise. That can be useful for climb cutting versus conventional cutting. And you got different things. This is on the course in G-code. So that's the basic concept. Now, here's something taken from an example somewhere. And a couple of things at the top part. It's an initialization routine, and it's kind of irrelevant as to what it is. It's defining some different terms and some different things. And you'll notice here that in red, there's parentheses added. Those are comments. I'm assuming that enough of you have done enough coding that you understand what that is. In this particular situation, it defines the home axis, but the stuff at the bottom, you begin to see stuff that I'm talking about. The G1, X52, Y57, Z10. It's a big machine. And the F is indicating, would be either indicating the speed to which to go to that position or the speed to run the spindle. The M typically would be the motor part, or if you're going to have one with other parts. This is actually a G code that's running a 3D printer. But it's the same as if you were running a milling machine. And these M codes lines indicate do something with the motor. And you can imagine that using the same G code that you run on a milling machine, they had to add extra codes for things like extruders on and off and stuff that didn't exist until 3D printers came along, and they will continue to have things added to them. Now, this is a example of what you would see if you walked into a machine shop, and you would see screens like this running their milling machines. And over on the left side, the G code runs past, and each line that is executed is highlighted. And like any computer, it can only do one thing at a time. So it runs those particular pieces of code, and then it goes and it runs and does its particular things, and it runs through there. This G code, even in the most modern pieces of equipment, is simply a text document, and it can be edited on the fly. You could go in, and if you didn't like, you wanted to change the position that something was going to go to, you would just simply change that code. It was something very similar, if you've heard of some nasty things that were done that made milling machines that were working on secret projects go ballistic. All they've done is gone in and were able to grab access through the internet and changed a couple of lines and made the motors run so fast they burned themselves out. To the right of that G code is the coordinates, where the head is in any particular part. And you can see X, Y, Z, and in this case, it could have a fourth axis. It could handle the fourth axis if it needed to. To the right is the toolpath. You'll see a picture of that in a minute. You can't see it very well on this one, but it actually gives a view, either you can generally set them to say, show me the view from the X axis, and then you would see the Y and the Z movements. You can show it from the Z axis, which is the most common, like a bird's eye view, and you will show the XY movement of the head. Down below are some other things. It says edit G code. I can go in and just simply type in another number for some of those parts of it. You got tools information and what size they're going to be, and the feed rate that is running. The spindle speed is the speed with which the cutter turns. All kinds of stuff. This is a screenshot of our CNC milling machine controls. And there on the left I have the toolpath, and you can see that toolpath. If you start at actually be the lower right, where you have two lines coming together, an arc and then another one that connects the two. This machine goes and it runs that long line at first, then it makes the three arcs that you see, Then it goes and moves back down to the bottom part and makes the movements that you see. You'll see the whole bit on the C. There's a set of videos on the CNC. But at the top, you see it has the same coordinate structure. It says the X, Y, and Z. And here it has the machine, also shows you the machine coordinates, which is where when the machine first wakes up, it uses sensors to define where X, Y, and Z are, and it zeros them, and then you set up the fixture coordinates, and where those at the top is where the machine head is at any given time. You put tools and feeds, and you can see the G code, and the program that's in light blue is the one being run, and you see the next one, and you see, if you look very carefully and enlarge this a little bit, you would see X, G1 or G0, and go to these particular coordinates. And of course, across the bottom, you got the control buttons. Watch the video to understand how this one works. Like ours, it just coordinates the X, Y, Z under computer control. You add the speed to it. It's very simple. But then generally the next thing that a CNC machine has, if you're going to pay some more money for it, is you can have an automated cutter change, because you don't generally make all of the parts just with a 1/4 inch end mill. Sometimes you need a 1/4 inch end mill, sometimes you need a 3/4 inch end mill, sometimes you need a ball nose, all kinds of different kinds. And to do that automatically rather than have an operator do it is very handy. And then you want to be able to maybe move the cutter. You maybe want to have multiple workstations. That's where we're talking about the tombstone. You want to have automatic feeds and loading materials on their own by computer. It can be, these machining centers can get very elaborate. Okay, got one last little topic, and I'm just throwing it in here because I want to be done with all the machining. And it is abrasive machining. There's a video on a grinder, an automated surface grinder. Well, it's not automated, but you can imagine it being automated. And there is a little bit about grinding that is a part of what we do. I was talking with one of the manager of one of the biggest machine shops in Fresno. In fact, it's won national awards for the work that it does. And you would think it's so highly automated. Machining centers, several 6-axis machining centers just all over the place. And he was saying that they got a visit from OSHA, and they got fined $5,000 because one of their grinders didn't have the tool rest in the right place. Here's this automated place, and a grinding wheel, bare bones, out there by itself. You would think they wouldn't even ever use it, wouldn't have it in the shop, but lo and behold, it's one of the most simple machines. But it's there. Anyway, you've got different abrasives in a grinding wheel or sanding situation, and the parts are very hard. Used to be they were made out of emery or even diamond or garnet. Garnet was a very popular one. You can still buy garnet sandpaper, in which case it truly is sandpaper. But around 1900, they started making artificial materials that were much harder. Now, you hear grain size, and the number, think of it as a window screen, and you could vary whether it was a very fine mesh or very coarse mesh of that window screen. Now, a big one would let a lot of flies in, so you want to make them small enough, but you don't want to make them too small that you block all the air. So somewhere in the middle is the right size for a window screen. Well, you could change those and sift sand. Let's just use garnet or any of these oxides. And you could end up making a pile of very fine grains, very middle grains, coarse grains, and it would depend on the number of lines, threads, if you will, per inch of the screen, or per distance. We're talking linen sheets and stuff, fine, if you just do an inch. But if you have big holes, you might have 40 lines per distance, and that's going to make it really big. And so if you have very small lines, you will have very fine grit that gets through there, and so you would have a higher number. I mention this because it always sounds kind of weird that the coarse grit for abrasives is a smaller number. The bigger the number, the finer the grit. Now, they don't do it with window screen type sieves anymore. They do it through cyclonic action. They blow the material into a cyclone controlled inside of a little cabinet, and it goes up circular. And the lighter the material, the further up it goes, and they kind of strip off pieces at different levels. Okay, you got these abrasives. You can put them as a free slurry. That means you put them on a tabletop and rub it in. You're polishing, basically. You're not going to use a free slurry with coarse material. You can adhere it to a belt with the resin, and we're talking a piece of paper or fabric, in which case you would call it sandpaper, or you can pack them into a wheel or stone held together by a bonding agent. That is a grinding wheel. How does it work? Whether it's sandpaper or, well, the polishing, you get a little bit there when you don't have a piece that's breaking. But when it's cutting, it looks a whole lot like the regular machining diagrams that we've been putting out here for a long time. You saw in almost all the other presentations. The difference here is you can see over on the right, you have a very sharp point out there, and it's doing a great job, but then it breaks. And then now your piece is going to kind of look at it, coming at it from a little bit backwards point of view, but it still is doing the same process. With grinding wheels, you can have a dense structure, or you can have what's called an open structure. And the difference has to be, and of course there's a middle side in there too. It depends on what you're going to use it for. And generally you buy a grinding wheel generally has 2 discs on it, because the motor is going to have 2 sides that it can work on. And you generally would have a dense one on one side and a open one on the other side. Now, what does that mean? Well, it has to do with how dense those things are packed around the material that holds it together. Got more of it, you're going to be able to do a lot more grinding on stuff, but you run into a little bit of a problem in that those, when you have that much together, they tend to individual chunks of the oxides do tend to break off. Actually, I think I have a picture of some of the oxides here in a minute. They tend to break off more frequently. And there's another reason that you'll see why there's a difference in what the advantages are. Now, what holds all these little chunks together can be vitrified, which is, you got ceramic clay material that is mixed up and fired in a kiln, and you've got this vitrified material that holds the grinding wheel together, or holds the particles within the grinding wheel. You can also have it with phenolic or plastic compounds, and that's what holds the parts together. Sandpaper, it is a misnomer to call it sandpaper. Garnet is a type of sand, and that's the only sandpaper that's available out there. And even then, you would want to call it coated abrasive sheets, because aluminum oxide is not sand. You can have the backing can be paper or fabric or even plastic. There's a bit to be said about how it's put on the bottom, the adhesive. You can, I've toured places where they make sandpaper, and it can be done a lot of different ways, but nevertheless, you gotta, those grains, which is the last part of this, gotta be stuck on the material, and you can do that with whatever glue you want. Now, how tight you get these pieces in, if it's more than 60% coverage, it's called closed coat sandpaper. If it's less than that, it's called open coat. And the advantage of that, and there's a picture of silicon carbide chunk and an aluminum oxide chunk. The open coat, you'll notice there's space between the particles. And the fact that they're kind of standing straight up, that is not an accident. When they manufacture sandpaper, they use an electrostatic system to cause those little buggers to stand up and have the best cutting surface at the top. But okay, you've got the open coat, and then you have the closed coat. Well, if you're sanding wood, you want to use an open coat, because each chunk is going to take off a bigger piece of wood than it will out of a piece of metal. With metal, you want to use closed coat, because the little pieces, metal chips, they're going to be pretty small and they will fall out. If you've ever sanded wood and your sandpaper clogs up all the time, that's because you're using a closed coat sandpaper, and the wood chunks are getting stuck inside between the sanding grit. So this is something to keep in mind, and you want to have different ones. Not all sandpaper is good for all types of material. I covered that in the materials class, so I'll leave it to you to catch that later.